Hello and welcome to this GeoStudio webinar, part of our Sigma W material model series. Today's webinar will focus on a new addition to Sigma W, the NorSand soil model. I'm Vincent Castonguay and I work as a research and development specialist with the Geoslope engineering team here at Sequent. Today's webinar will be approximately 60 minutes long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will also be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists comprised of several products. The range of products allow users to solve a wide array of problems that may be encountered in these fields. Today's webinar relates specifically to Sigma W. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the Geoslope website. There you can find tutorial videos, examples with detailed explanations, and engineering books on each product. The successful use of numerical tools generally comprises 6 steps which, broadly speaking, are: first, conceptualization of the physical system and expected response; second, selection of the relevant physics; third, parameterization of appropriate constitutive models; fourth, application of boundary conditions; fifth, solving the physics subject to the boundary conditions and constitutive laws; and sixth, verification of the results. Today's webinar focuses on step 3 of the modeling process. More specifically, we are going to explore how to parameterize the NorSand soil model in Sigma W. This webinar will be divided into 3 parts. We will first review the most important aspects of the NorSand model. We will then explore the calibration of the model's input parameters. Finally, NorSand's implementation in Sigma W will be presented. Underlying many aspects of this webinar will be practical examples of triaxial compression tests. Users are encouraged to visit Geoslope's website to download the triaxial test on NorSand soil example to serve as a reference. A set of laboratory data published by Jeffries and collaborators is used throughout this webinar to evaluate NorSand's performances using real-life examples. This dataset includes 7 trained and 5 untrained triaxial compression tests performed on the Fraser River sand. These trained and untrained triaxial tests were performed at a variety of initial densities and stresses, giving us the possibility to use NorSand for dense as well as for very loose soils. Let us start this webinar by reviewing the important basics of NorSand. NorSand is a constitutive model created by Mike Jeffries in 1993, which has been updated and upgraded considerably through the years. It is a soil model specifically designed to correctly simulate sand behavior for a variety of states, from dense and dilatant samples to loose and very contractive ones, such as what we see here, where static liquefaction is simulated by the model. Although NorSand's primary application is geared towards sand behavior modeling, it is also well equipped to deal with other materials, such as silts and tailing materials. NorSand was effectively used by the Fundao Tailings Dam Review Panel in 2016 to investigate the possible causes of failure of the Fundao Dam, built using a varied and complex array of soil materials, showcasing NorSand's flexibility. NorSand is a soil model based on critical state soil mechanics. Very briefly, this theory stipulates that as a soil is sheared, for example from point A to point B on this figure, it will move toward its critical state, a unique point in mean effective stress, deviatoric stress, void ratio space, where it will undergo very large shear deformation for any small shear stress increment. The state parameter, denoted by the Greek letter psi, is a critical component of NorSand. The parameter is a measure of the distance, in terms of void ratio, to the critical state line at constant mean stress. It represents a clever way to express both density and mean stress state in one simple parameter. By definition, if the state parameter is negative, the soil is dense compared to its critical state, meaning that it will have to dilate to reach its critical state. Conversely, a positive state parameter denotes a loose soil that will contract when sheared. The magnitude of the state parameter also indicates the density in a relative sense. A large positive psi, for example, indicates a very loosely packed soil. The last important concept to review before looking at NorSand's input parameters is dilation. Let us consider this volumetric deformation plot, which I borrowed from one of the drain triaxial tests performed on dense sand available in our dataset. As is typical for dense sands, we see an initial contractive phase associated with positive volumetric deformations. At around 2% of vertical strain, the maximum positive volumetric strain is reached, and the soil starts to dilate, or expand if you will. At around 3% of vertical strain, the accumulated volumetric strain becomes negative, meaning that the sample's volume is now larger than it was at the beginning of the test. Another way to look at the same data is to calculate dilation. Dilation is the change of volumetric strain divided by the change of deviatoric strain. This plot shows how dilation evolved during the test. Notice that dilation is initially positive, meaning that the change in volumetric strain is positive compared to the accumulating deviatoric strain. In other words, the sample is contracting. At around 2% of vertical strain, we find point A again, where dilation becomes negative, inverting the volumetric trend observed in the first plot. An interesting point about dilation is that it closely relates to the critical state. If we were able to continue to shear the sample in the laboratory to very large deformations, we would see that dilation will tend towards zero and that the slope of dilation will also tend towards zero. These two conditions are the exact definition of the critical state. This is, in fact, one of the several ways to express the critical state conditions. The maximum negative dilation reached during a test is called D-min and is of particular importance in NorSand. As we see in this figure, which includes data for 20 sands, maximum dilation is closely related to the state parameter. Denser soils will show larger maximum dilation. Maximum dilation is in fact directly proportional to the state parameter for any given sand. It is possible to reduce the scatter of this dataset by normalizing the state parameter using a constant, which would be calibrated for each sand. This constant is called Xi, the state dilatancy parameter, one of NorSand's input parameters. Throughout NorSand's formulation, maximum dilation is used as a driver to pace deformations. As this webinar only covers some of NorSand's most important aspects, interested users should refer to the Static Stress Strain Modeling with GeoStudio book, available on GeoSlope's website, and the Soil Liquefaction, a Critical State Approach book for a more thorough description of the model than what is presented here. Now that we have reviewed some important foundation blocks of NorSand, let us review the model's input parameters and their calibration. Elasticity in NorSand is defined using three parameters: the elastic shear modulus at the reference pressure, the elastic exponent m, and Poisson's ratio nu. The first two are used together to define a stress-dependent elastic shear modulus G. The exponent m can take values from 0 to 1 in order to establish the type of stress dependency desired. If m is set to 0, the shear modulus will be constant, irrespective of stresses. Or, the opposite, if m is set to 1, the shear modulus will be directly proportional to the mean stress. Real sand behavior tends to fall midway between these two extremes, and m is often taken as 0.5. Poisson's ratio is used to define the elastic bulk modulus, using the value of the elastic shear modulus. Poisson's ratio has limited impact on the outcome of large deformation simulations where plasticity will govern the soil's behavior. For sands, it is generally safe to assume that this constant will take values between 0.15 and 0.25. Specifically for the Fraser River sand from our dataset, a Poisson's ratio of 0.2 and an m value of 0.47 were used. The position of the critical state line is defined in NorSand just as it is for any other critical state soil model, generally as a straight line in the void ratio, natural logarithm of mean stress space. The altitude of the critical state line at a mean stress of 1 kPa is defined using the parameter capital gamma, while its slope is defined by lambda. Note that there are no strict shape the critical state line should take, as we will see further on in this webinar. The final set of NorSand parameters relates to plasticity, namely the critical state ratio, the volumetric coupling coefficient, the state latency parameter, the plastic hardening modulus components, and an optional additional softening index. Of these 6 parameters, 3 are directly calibrated using triaxial compression test results. This is in addition to the critical state line parameters, which are also calibrated using triaxial test results. The calibration of these 5 parameters can easily be done using an Excel spreadsheet and doesn't involve any numerical simulations, as we will see later on. As we just discussed a moment ago, we generally simplify our lives by assuming that the elastic exponent m and Poisson's ratio are taken as constants when calibrating the model, rather than undergoing a strict calibration process. Another simplifying approach we generally take is to avoid using hy and s when beginning a calibration process, as these parameters are optional in NorSand. This then leaves us with 2 remaining parameters that need proper calibration: the elastic shear modulus at the reference pressure and the base value of the plastic hardening modulus. In an ideal scenario, we would have laboratory measures to guide the calibration of the shear modulus. However, this is rarely the case, and we must then proceed to calibrate this value in tandem with the hardening modulus using NorSand simulation results. But before we jump into NorSand simulations, we must first calibrate the critical state line parameters. Here are 12 triaxial compression tests from our dataset, expressed as void ratio mean effective stress plots. Notice that some tests are straight lines here. These are the undrained tests, during which the void ratio cannot change because volumetric deformations are prevented by the undrained boundary condition. I have identified the end of each test by a black square. Although our job here is to fit the critical state line through this data, one must be careful not to confuse the meaning of the end of a test. It is not necessarily because a test has reached its end in the laboratory that it has also reached its critical state. In fact, reaching critical state in a common laboratory setup is quite rare. Let us look at a particular test to illustrate this important point. Here are the test results for this drain triaxial compression test performed on dense sand. This test ended at 20% of vertical or axial strain, as is common for triaxial tests, but was still short of reaching its critical state. There are many ways to notice this. One of my favorite methods is to look at the dilation plot on the bottom right. Notice that at the end of the test, dilation is not equal to 0. Neither is the slope of the dilation curve. To reach these 2 conditions, which is necessary to reach critical state, the test would have had to continue for quite a while. This is unfortunately impossible in the laboratory, because as large deformations occur, strain localization takes place and the sample is no longer deforming homogeneously. As a general rule of thumb, it would be safe to assume that at 20% of vertical strain, critical state is very rarely achieved. Back to our series of results then. We should expect that this blue curve would still need to experience some level of deformation before it really reaches its critical state. In this case, this would mean that its void ratio should continue to increase. We should do a similar exercise of cautious judgment for each end of test before attempting to place the critical state line. Assuming that the critical state line would be straight in this void ratio log of mean effective stress plot, would yield the following best fit. We are able to achieve a very good fit for the lower right part of our body of data. However, notice that 2 undrained tests on the upper left portion of the plot are way out of place. Their endpoints are far from the critical state line. These 2 tests are loose sands, which underwent static liquefaction. If we were to use this critical state line position for our simulations, we would inevitably end up with bad fitting results for these tests, hence negating NorSand's potential capability to simulate static liquefaction. Fortunately, by using a curved critical state line, we can achieve a much better fit. As I stated earlier in this webinar, there is no particular reason to assume that the critical state line should be straight, other than because it is convenient and easy to adjust. In some cases, a curved critical state line is desired because this is what the data simply requires. For these special cases, sigma w can accommodate a curved or a linear critical state line. After the critical state line is defined, we can then revisit each triaxial test to calculate how the state parameter evolved during shearing. For this particular test, starting at point A and ending at point B, the state parameter will show that the sample was dense, since psi is less than 0, and, after 20% of deformation, ended up quite close to its critical state, which by definition would happen when psi and the slope of psi are both 0, similar to dilation. Now that our critical state line parameters have been chosen, we can move on to calibrating 3 of the plasticity-related parameters. We have already seen that volumetric deformation plots can be expressed in terms of dilation. There is, however, another way to look at this same data. Instead of looking at dilation as a function of vertical strain, let us look at stress ratio, eta, as a function of dilation. As a reminder, the stress ratio is simply the deviatoric stress divided by the mean effective stress. At the start of an isotropic triaxial test, the stress ratio is 0. On this plot, however, the first recorded dilation value is point A, which is already at a stress ratio of 0.4. This is simply caused by dilation being calculated as a change in deformation. Hence, it cannot be calculated on the first step of a test. As the test progresses, the stress ratio rises at the same time as dilation becomes more negative. Maximum dilation, d min, will eventually be reached, which would also coincide with the maximum stress ratio, eta max. To calibrate some of NorSand's input parameters, we must record this pair of values, as well as the value of the state parameter when this maximum dilation is reached. Another interesting piece of data available on this plot relates to the critical state ratio, MTC. After maximum dilation has been reached, the soil will fall toward its critical state, which would be the y-intercept on this plot at very large deformation. This is one of the several methods for determining the critical state ratio. For each drain triaxial compression test performed on dense sand in the dataset, we would want to identify these 3 important points: the maximum dilation, the stress ratio at maximum dilation, and the state parameter at maximum dilation. It is important that only dense samples are used for this step, since there wouldn't be any maximum dilation to identify for a loose sample by definition. For our dataset, this process would yield the following values. By plotting these together on 2 separate plots, we can see trends emerging which will allow us to determine 3 of NorSand's input parameters. On plot A, which is the maximum stress ratio as a function of maximum dilation, the y-intercept corresponds to the critical state ratio, MTC. The slope of this best fit line would then be related to the volumetric coupling coefficient n. On plot B, which is the maximum dilation as a function of the state parameter at maximum dilation, the slope of the best fit would correspond to the state dilatancy parameter ΣTC. Notice that both ΣTC and the critical state ratio MTC have the TC subscript. This indicates that these parameters are specific to triaxial compression. The corresponding internal model parameters vary when loading conditions depart from triaxial compression. Also note that the best fit line on plot B should pass through the origin, as by definition, dilation should be 0 when the state parameter is 0. Now that most of NorSand's input parameters were defined, we are only left with parameterizing the elastic shear modulus at the reference pressure and the base value of the plastic hardening modulus. While the role of the elastic shear modulus is obvious, it is less so for the hardening modulus. The plastic hardening modulus H controls the rate of hardening of the yield surface. H is built using 2 of NorSand's input parameters, a base value H0 and a dependent value Hy, which is optional and used to impose a dependence on the state parameter. We will see later on how this can be used to generalize the model. Notice that when Hy is equal to 0, which is the default value, h is simply equal to h0. The hardening of a yield surface refers to a change in the yield surface size and position. Here is NorSand's yield surface. It adopts a similar teardrop shape as the original cam clay model. The yield surface delimits the elastic from the elastoplastic region. A stress point that is located inside the yield surface will only produce elastic deformations upon loading. A stress point located exactly on the yield surface will produce both elastic and plastic deformations. And finally, a stress point located outside the yield surface is inadmissible. To reach a stress point at C, the yield surface would have to expand, a mechanism called hardening. It is precisely this aspect of the model that the plastic hardening modulus H controls. How much hardening occurs for a given plastic shear strength increment is determined by H's value. This parameter is calibrated using a trial and error procedure using NorSand simulation results. Now that we have reviewed the input parameters required to use NorSand, we can move on to using the model in sigma W to complete the calibration procedure. A good practice before jumping into sigma W to calibrate the model is to properly organize our test data. This can easily be done using Microsoft Excel. Here is how I like to set this up. This workbook contains all the laboratory results that I have available to adjust NorSand's parameters for the Fraser River sand. I created a summary sheet where each test is identified. I also identified the initial conditions related to each test, as I will need these values to set up the sigma W simulations. Finally, the known input parameters for NorSand previously determined are also indicated. These will be common to all the simulations. The parameters identified in red are those that need to be adjusted using the simulation results from sigma W. In this other sheet are the various plots that help me fit the NorSand parameters that were already discussed earlier. You will recognize some of these plots. Finally, all the other sheets contain the laboratory test data. Each sheet corresponds to one single test, where a few plots help me visualize each test. For a drain test, I like to view the stress point plot, the stress path plot, the volumetric deformations, and the state parameter evolution. For an end-drain test, instead of the volumetric deformations, I plot the pore water pressure. Let us use the test identified as CID D113 to start the parameter adjustment procedure in sigma W. This test is a drain test on dense sand. Since there are already many tutorials available on GeoSlope's website on how to set up a triaxial test in sigma W, I will go through these steps swiftly. Feel free to download one of such examples from our website if you are unfamiliar with some of the steps featured in this part of the webinar. First, I set up the project geometry for a triaxial test. I use the 2D axisymmetric geometry to take advantage of the triaxial sample's cylindrical shape. This allows me to only model a quarter of the sample. I then create the sigma W load deformation analysis to apply the stresses that exist at the end of the consolidation phase. I create a simple isotropic elastic material model here, as the deformations are irrelevant for this step. Our goal is simply to establish the proper stresses that exist at the start of the triaxial test. I apply boundary conditions to represent the confining stresses to which the real sample was subjected. A single higher-order element with reduced integration will suffice given that there are no special variability of stress and strain. I can start the analysis and verify that the stresses are correctly applied to the sample. The next step is to create a new sigma W load deformation analysis to perform the shearing phase of the triaxial test. Tolerable errors and number of steps are adjusted to produce better results when using NorSand. A NorSand material model is created, and the parameters determined in the previous part of this webinar are entered. Then, a first try for defining the 4 missing parameters is done. We haven't discussed the overconsolidation ratio yet. The overconsolidation ratio, OCRP, is the ratio of the current over the historical maximum mean effective stresses. The UI input displays the subscript P to remind us that the ratio is defined in terms of mean effective stress. For sands, the OCR is normally never very high, but it is generally correct to assume that a little overconsolidation exists in a triaxial sample. A value of 1.1 is used here. For sands, values between 1 and 1.3 are normally expected and generally will not have an overly important impact on the simulation results, especially for drain simulations. Next is the shear modulus at the reference pressure. There are many ways to generate a first guess of this value. Use whichever method you prefer. From my geotechnical engineering courses back in university, I have always remembered that Young's modulus for sands can be approximated using the relationship N, the SPT blow count, times 2000. Young's modulus divided by 2 times 1 plus Poisson's ratio will then yield the elastic shear modulus. For Poisson's ratio roughly estimated to 0.25 to keep digits easy to work with, This would mean that I could estimate the shear modulus G as being n the SPT blow count times 800. Let us estimate that our somewhat dense sand could have an SPT blow count of 25, which would yield an estimated shear modulus of 20,000 kPa. While an n value of 25 would technically not be considered dense in the field, it would probably correspond to a dense sample built in the laboratory for a triaxial test. This is of course just a rough estimate to get us going. I like this method because I can genuinely get this estimate in my head just by remembering this simple relationship. Next is the plastic hardening modulus, H. As I said earlier, it is good practice to first neglect the effect of the state parameter psi on the hardening modulus by setting Hy to 0. We will come back to this value later, but for now, we assume that the hardening modulus is simply equal to H0. The plastic hardening modulus value generally sits between 20 to 400, and a good first estimate for it is H is equal to 4 divided by lambda, the slope of the critical state line. In our case, since we use a curved critical state line, lambda is not defined, so let us just use a value of 60 as a starting point. Finally, let us consider S, the additional softening index. This is a feature which helps NorSand correctly simulate the response of loose soils being loaded under undrained condition. S can take values from 0 to 1, but is generally used with either 1 or 0, like an on-off switch if you will. For any drained test, S should always be kept to 0. For a non-drained test, if the sample is dense, for example if the state parameter is smaller than 0, then S should also be kept to 0. However, if the sample is loose, for example if the state parameter is larger than 0, then S could be non-zero. I will show the effect of S equal 1 for some undrained examples later on. For now, since the test we are calibrating is drained, S will be set to 0. Back to sigma W, we can now input the missing parameters we just discussed to complete our definition of the NorSand material. The last step remaining before solving this analysis is to create the boundary conditions needed to perform a triaxial compression test, meaning that the top part of the sample must be made to move downward. By creating a y displacement function, I can ensure that the top nodes will move down by 0.01 meter, which corresponds to 20% of vertical deformation for the size of our sample. I can now go ahead and remove the stress boundary conditions that were created for the stress initialization step, as we don't need these anymore. The parent analysis, which this current analysis depends on, will transfer its stress conditions to its child. I'll now apply the newly created displacement boundary condition to the top of the sample. As a side note, the function should be defined over an elapsed time that is commensurate with the duration of the analysis, for example 1 day. That way, the number of steps used to simulate the total vertical straining can be varied without having to change the boundary condition. We are now ready to solve the analysis. Once this is done, I can create plots to view the data and to export it to Excel to compare the NorSand results with the laboratory data. To do so, I can select all my plots, which are conveniently expressed in terms of vertical strain, and right-click on a plot to select Copy Graph Data. Once plotted alongside the laboratory results, I can visually inspect the simulation results and evaluate the model's performance. In this case, it looks like the model stress-strain curve on plot A, the orange curve, is too soft compared to the laboratory results, the green curve. It is, however, worth pointing out that this first estimate already provides a very acceptable fit compared to the laboratory data. This showcases the benefits of being able to adjust most of NorSand's parameters straight from laboratory data. By returning to GeoStudio and adjusting the indicated parameters, I can obtain what we will call the best fit. Judging that simulation results represent the best fit possible is of course quite subjective, and there might be various combinations of parameters that will lead to similar fits. Care must be taken to avoid using unrealistic values. For example, one can hardly expect OCRs larger than 1.5% or shear moduli larger than 200,000 kPa. When I'm satisfied with the fit I obtained, I want to leave a trace of the final parameters I use for this specific test. To do so, I will return to my Excel summary worksheet and input the chosen parameters under the test I was working on. I will then proceed similarly with all the tests I have in hand, using the same steps I just described. I will use the same geometry, but will add new stress initialization and triaxial compression phases for each test. The stress boundary conditions are specific to each test. In addition, the NorSand material models are defined uniquely for each test, representing the appropriate initial conditions indicated in my Excel summary worksheet. I will follow the same procedure where I make a first guess of the missing material parameters and proceed to adjust them until I reach a satisfying fit. We will work on normalizing these first guess parameters at a later stage of the procedure. I will finally record the best fit parameters for all the tests in my Excel summary workbook. You will notice that for 3 of these tests, the additional softening index was turned on. This can be done since these tests respect the requirements that they must have been performed in non-drain conditions for loose soils. Here is an example of the effect turning the additional softening index can have on such tests. These are the simulation results we obtain when we use the default S value, which is 0, for a test where static liquefaction is observed. We can see that the response is much stiffer for NorSand than for the laboratory results. In particular, notice on plot D how NorSand is still very far from critical state, where the state parameter psi will be 0, while the laboratory results, on the contrary, very quickly reach critical state. By simply turning the additional softening index on, we can get these results instead. NorSand is now able to capture every aspect of the static liquefaction behavior very nicely, producing large pore water pressure that drive the mean stress to very low values, generating large deformations for minimal stress increments. Although the additional softening index should only be used after thoughtful consideration, it can greatly help to properly simulate some more complex aspects of loose soil behavior. Back to our Excel summary worksheet. Now that we have defined the NorSand input parameters for every laboratory test we had available, we can explore the possibility of generalizing some of the input parameters to obtain a set of parameters that would be as consistent as possible across all the tests studied. This should be done in order to render our NorSand material more flexible. In an ideal situation, all the input parameters should remain the same, no matter what the test conditions we encounter are. Let us focus on the elastic shear and plastic hardening moduli, and how these two input parameters seem to depend on the initial state parameter. This would help us generalize our inputs to make NorSand easier to use in real-life simulations. I have plotted the plastic hardening modulus on the left and the elastic shear modulus at the reference pressure on the right, both as a function of the initial state parameter. These plotted values are the best fit parameters I have adjusted using sigma W. As it can be expected, both moduli show a dependency on the initial state parameter. For both, denser soils will yield larger moduli. By passing a linear regression line through both series of data, I can define simple relationships which can help automatically choose moduli values that will yield good simulation results, no matter the initial conditions. Specifically for the plastic hardening modulus H, the two parameters of the linear regression curve can be used directly in sigma W as input values that will directly take into account the initial state of the soil. The next version of Sigma W, to be released during the spring of 2021, will also feature similar state-dependent capabilities for the elastic shear modulus. Let us take a final look at the Excel summary worksheet. Now that I have defined state-dependent relationships for both moduli, I can record the chosen H0 and Hy values. I can then use the elastic shear modulus relationship to calculate the generalized shear modulus at reference pressure for each test. This allows me to finally define a complete NorSand model that is almost entirely dependent on the initial state for its initial parameters. A case could very well be made to also adopt a single value of OCR for all the tests, say 1.15 for example. The only parameter that would then be needed to be adjusted by the user would be the additional softening index S that still needs to be turned on manually for undrained loading of loose soils. Other than these caveats, the NorSand model we established provides all the necessary parameters to properly simulate the behavior of the Fraser River sand for triaxial loadings that include dense as well as loose initial states, and undrained as well as drained conditions. To showcase the power of the procedure we just completed, let us compare simulation results for the best fit possible against the final fit using the generalized expressions for the elastic shear and plastic hardening moduli for a few tests. These are the simulation results for a drained triaxial test performed on dense sand. The green curves are the lab results, and the red curves are the NorSand simulations for Sigma W with parameters chosen to produce the best fit possible. Finally, the dashed blue curves are the Sigma W results using the input relationships developed in the preceding steps that use the initial state parameter to initiate the shear and hardening moduli. The two NorSand simulation sets are very close to each other, and overall, very close to the laboratory results. Even when using the input relationships, NorSand clearly captures the soil behavior. As expected, the dense soil shows some initial contraction followed by important dilation that will bring the soil closer to its critical state at large deformation. Here is an undrained test performed on loose sand, where, as in other tests showed earlier, static liquefaction is involved. Again, the NorSand simulation using the state-dependent input relationship are very close to the best fit possible. Very contractive behavior is observed, and the soil is quickly reaching its critical state. Both simulations closely follow the laboratory soil behavior and correctly stimulate static liquefaction. This is a really great example of the strength of NorSand. With a constant set of input parameters coupled with state-dependent relationships, one can simulate dilatant as well as very contractive behaviors. As a last example, here are the simulation results for a non-drained loading on dense sand. Again, the Sigma W simulation results using the state-dependent relationships are very close to the best fit possible. Both simulations correctly follow the laboratory results, where an initial contraction phase, accompanied by a positive pore water pressure generation, is followed by a dilatant phase, during which negative pore water pressure are generated. That concludes this webinar, part of the Sigma W material model series. Three main topics were covered during this presentation. At first, an introduction to NorSand was presented, where the basics of this soil model were discussed. The various input parameters needed to use NorSand in Sigma W were examined, with a special focus on how most of them can be adjusted using triaxial compression results directly, while some others need simulation results from Sigma W to be properly defined. Finally, we considered how to use NorSand in Sigma W. Toward the end of the presentation, a special focus was put on how to generalize NorSand's input parameters to create a complete and flexible state-dependent model, which represents one of NorSand's strengths. Our team of development engineers is already hard at work to provide new improvements to NorSand in the next version of Sigma W that should be released this spring. Users will notably be able to define the elastic shear modulus at reference pressure as a function of void ratio. It will also become possible to use the state parameter as an input instead of the void ratio. If you'd like some new features and capabilities added to NorSand in Sigma W, don't hesitate to make suggestions by submitting support requests. We have now reached the end of this webinar. A recording of the presentation will be available to view online. Please take the time to complete the short survey that appears on your screen so that we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.